In this video, we're going to look at increasing and decreasing functions as well as critical points, max and min values. The first thing that we should start off with is distinguishing between a vertical asymptote and a vertical tangent. Students often mistake the two, so it's important to review the difference between them. So a vertical asymptote is when there is a restricted value for x. That is, the value of x would cause the denominator to equal to 0. So we have these breaks in the domain. That's a vertical asymptote. A vertical tangent is something entirely different. A vertical tangent occurs when the tangent to the curve at that point would be vertical. The first derivative will be undefined in this case, and the sign of the first derivative will not change before and after that x value. So right at this one point right here, we see the slope goes vertical, right? And if I try to find the slope of a vertical line, well, if we think about what slope is y2 minus y1 all over x2 minus x1. If you see right here, if I try and find the slope of a vertical line, these two values will be the same, so I'll end up with 0 in the denominator, and that's why the first derivative of a point where the tangent is vertical is undefined. Okay, when sketching curves in MHF4U, we use the following concepts as well. We talked about intervals of increase and decrease, x-intercepts, end behavior, asymptotes, and then solving inequalities, signs, and factor tables. So we're going to use this for this unit in curve sketching. We're going to use all these concepts, but let's focus right now on intervals of increase and decrease. So intervals of increase and decrease in the first derivative. So if a function is increasing, I'll give you an example of a curve that's increasing. So this is a curve and it's increasing. If we were to go to take the tangent of that, okay, we can see that the tangent has a positive slope because it's going from quad 3 to quad 1, right? So it's got a positive slope. So then the first derivative is positive. Okay, but if you have a curve that is decreasing like this or something like that, and then we do a tangent along right here, let's say, we can see that we have a negative slope. So the first derivative is negative. If given the function f of x is equal to x cubed minus 6x squared, we can look at the first derivative and determine where the function is increasing or decreasing using either a sign table or a sketch of the first derivative. So again, we repeat right here, if the first derivative is positive, the function is increasing, and if the first derivative is negative, the function is decreasing. So let's find the first derivative and complete a sign table and a sketch. So if we look at this function right here, the first derivative should be 3x squared minus 12x. Okay. If we wanted to factor that, we would factor that as follows. 3x x minus 4. Then what I need to do is now that this is factored, I look at where my zeros are. And I've got x is equal to 0 and x is equal to 4. I can use these zeros and this function to create a sign table. And here's my sign table. So we see that we have the zeros along the top and the intervals between the zeros. And then on the left-hand side, we have the various factors. So 3x, x minus 4, and then we talk about what the overall sign is. Well, let's go ahead and start filling this in. Okay, for x is less than 0, this is negative and this factor is negative. So overall, multiplying those two factors together, the overall derivative is positive. Then we have right here in this interval, this is going to be positive, that's going to be negative, and the first derivative will be negative. Positive, positive, positive. Okay. So if I look at this right here, I can see that my first derivative is positive for the interval below 0. So x is increasing when the function is below 0, or for x values below 0. The first derivative is decreasing between the first derivative is negative, so the function is decreasing between 0 and 4. And the first derivative is positive for x values greater than 4, so that means that the function is increasing. Now we can also sketch the first derivative. Now make sure that we're making that very clear. We're sketching the first derivative here. And if I sketch the first derivative, well, the first derivative is a quadratic. Okay, so I'm going to go ahead. I'm just going to quickly make a little set of axes here, okay? And my zeros are at 0 and 4 for my first derivative, and I can see it's got a positive leading coefficient, so it opens up right here. Okay, something like this. Okay, so that tells me that for x values, that's 0, that's 4. Okay, so I see that my first derivative is positive from negative infinity to 0, and my first derivative is positive from 4 to infinity. My first derivative is negative between 0 and 4. So what I would say is, therefore, f at x is increasing for x element of negative infinity to 0 and 0 to 4, and decreasing for x between 0 and 4. Okay, and so we actually literally just wrote this conclusion out on the next page. So when x is less than 0 and when x is greater than 4, our function's increasing, and it's decreasing between 0 and 4. And again, that is all done by looking at the sign of the first derivative, or sketching the first derivative and finding when the first derivative sketch is positive and when the first derivative sketch is negative. Both methods are acceptable. What about at x is equal to 0 and x is equal to 4? Well, these are called critical points. So we now move on to the critical points and first derivative test portion of this lesson. So a critical point or critical points are points on a function where the derivative is either 0 or undefined. The x-coordinate at one of these points is called a critical number. Note, these are points that exist on the function, not, for example, locations of vertical asymptotes. So critical numbers must exist. Okay, so that's a key point right there. They must exist on the function. They cannot be a restriction. Cannot be a restricted value. Okay, so there's two main ideas here. If the first derivative is equal to 0, then it could indicate a local maximum, a local minimum, or a point of inflection, where the function is changing from opening up to opening down and vice versa. I'm going to make a little point right here, a flattened point of flexion rather, not infection, flattened point of inflection. If the first derivative is undefined, we could end up with a cusp or a vertical tangent. So that's undefined, we get a cusp or a vertical tangent. After finding a critical point, we can use the intervals of increase and decrease to identify the type of the point. Okay, so let's take a look at this right here. If the function goes from increasing, so I'll draw this right here, the function's going from increasing and the function is going then to decreasing, you can see this point right here where the first derivative is equal to 0, that point is going to be a maximum. Okay, vice versa, if it's going from decreasing to increasing, this point right there is a minimum. Okay, if there is no change, the point is a flattened POI. Okay, so in that case right here, look, it's going increasing, flattens out, and it's still increasing. Alternatively, decreasing, flattens out, decreasing, but it's called a flattened POI, or flattened point of inflection. Now it says label each of the above bullet points with the letter represented on the graph. Well, here we go. We've got decreasing to increasing. That's going to be a minimum, so that's A. Over here, we've got increasing, and then it increases again, but it goes flat. That's a flattened POI. And then if the function is increasing to decreasing, that's going to be a maximum, and that's C. Okay, for critical points where the first derivative does not exist, if the function goes from increasing to decreasing, or vice versa, then the point is a cusp. You can see right here, if you take a look at our first derivative, right before the cusp, first derivative is positive. Right after the cusp, first derivative is negative. So that point right there, remember, first derivatives don't exist on cusps, but since the sign changes before and after for the first derivative, the point is a cusp. if there's no change, so we can see right here, like the function's increasing, so the first derivative is positive. Right here, the tangent goes vertical, and so there's no slope of a vertical line. It's undefined. And then it continues to increase. The point is basically like a vertical, like we get a vertical tangent. Point where a vertical tangent exists. Okay, let's move on to doing some examples here. And remember that you can use either a sine table or a sketch for the first derivative to determine and classify the critical points. Okay, example 1 says, find and characterize the critical points for this function. For this example, use a sketch of the first derivative. Always start by finding the first derivative and then determining the values of the critical points, either 0 or undefined. So the first thing I'm always going to do is I'm going to look at the function right here. I'm going to rewrite the function, and I'm going to look for any discontinuities. Well, this is a polynomial function. X doesn't appear in the denominator anywhere, and there's no restricted values, so we say no restrictions. And the reason why I say no restrictions, this means that any X value can be a critical point and critical number. Okay. All right, so what we're going to do here is we're going to take the first derivative, and then we are going to factor it. Okay, so there is my first derivative right here. I factored out of 12, and then I factored the trinomial, and I got this right here. Now, what I'm going to do is I'm going to set y prime equal to 0 to find the critical numbers. So we are going to find the x values that make the first derivative equal to 0. You can do it by inspection just by looking at it right now, but why not? Let's go ahead and set it equal to 0. Okay, so I set y prime equal to 0 to find the critical numbers. There we go. And so I find that my critical numbers are x is equal to -1 and x is equal to +2. And so the question right here said, it asked me to use a sketch of the first derivative to characterize the critical points. So let's just take a look right here. Okay, I'm just going to do a really quick sketch of this first derivative here. Okay, it's a quadratic, it's got a positive leading coefficient, so that means that it's opening up, and it's got zeros at -1 and 2. So here I go -1, and then over here I'll say this is 2. And so this is the sketch of my first derivative right here. Okay, so at -1, I can see I'm going from a positive value to a negative value, and at 2, I'm going from negative to positive. So repeating that information over here, at -1, I went from positive to negative. So I went from increasing to decreasing. Okay, so that means that -1 is a maximum, and then I can plug -1 back into my original function right here, and the y value that I get there is 15. Okay, so that is a max. Okay, so there's one critical point. At 2, we can see right here, it goes from negative to positive. So if I think about that, okay, so let's write negative to positive. So it goes from decreasing to increasing. Okay, so that means 2 is going to be a minimum. So 2, and then again, I plug 2 back into my original function. So plug 2 back into here to find the y value, and that would be -39. Okay, and so there we go. So again, take the function, find the first derivative, find the critical numbers, and either sketch or use a sine table. In this case, we use a sketch to look at the behavior around the zeros. And then we saw that because of the sign change, that made this one a max and this one a minimum. Example 2, find and characterize the critical points for this right here. For this example, use a sine table of the first derivative. So in this case right here, we know that this is continuous. It's a polynomial function, so xer for the domain. Any value of x could be a derivative. Sorry, any value of x could be a critical number, rather. Okay, so I'm going to look at this right here. So I go y prime is equal to 3x squared plus 6x plus 3. So that's the first derivative. Factoring out a 3. Okay, and then I get y prime is equal to, I see that's a perfect square trinomial, 3x plus 1 all squared. Okay, I'm going to set y prime equal to 0 to find my critical points. Setting y prime equal to 0, I get 0 is equal to 3x plus 1 squared. So therefore, x is equal to -1. That's a critical number. Okay, so this is a critical number. I sub -1 back into this function right here to find the y value of that point. So I go -1 and sub that in over here. So -1 plus 3 times -1 squared plus 3 times -1 plus 3, and I get 2. So just to be clear, this is what's called the critical number, and this is called the critical point. Okay, so now what I'm going to do is I'm going to construct a sign table around this critical number. And so this is the only value that gives me 0, so I'm going to say x less than -1, x greater than -1, and then there's only really one factor here, and that's 3x plus 1 all squared. Well, because this is all squared, it's always going to be positive. And so that means that my first derivative, or y prime, whatever you want to say, is always going to be positive. And so there's no sign change. Here we go. No sign change across critical number. And the critical number that gives you 0. So let's see, a critical number where that makes the first derivative equal to 0 and there's no change in sign, then we have a flattened POI. Okay, so therefore, -1, 2 is a flattened point of inflection. Okay, and so what we mean by a point of inflection, that's basically where it's going like concave down, flattens, and then goes concave up. All right, let's look at the second last example, actually. One thing that I added over here is just include the restricted values of x in the sign table when you go to construct a sign table for this. Okay, so what we're going to do is I look at this right here, and I see that x cannot be equal to -1. So that means that -1 is not a critical number because there's a vertical asymptote at that point. All right, I'm going to go ahead and I'm going to find my first derivative for this. And so if I go ahead and use the quotient rule, I can come up with the following. So there is my first derivative using the quotient rule. I note right here that x can't be equal to -1. It's not a critical number, so then my critical numbers are anything that makes the first derivative equal to 0. So remember, a fraction can only equal to 0 when the numerator is equal to 0. So I just look at the numerator right here. I don't take into effect the denominator because denominator doesn't make a fraction equal to 0. So right here I see that x could be -3 and x could be 1. Right? Those are going to be my critical numbers. All right. And so, yeah, so if I have these right here, okay, so x is equal to -3 and 1, then I'm going to construct a sign table that has the following along the top. X less than -3, and look, it says include restricted values in the sign table. So -3, x is greater than -3 but less than -1. Okay, x is greater than -1 but less than 1, and then x is greater than 1. And then I use my different factors here. So over here I've got x minus 1, x plus 3, x plus 1 squared, and then overall my first derivative. And then I start putting in signs. Okay, well, I know that this is the case right here. Okay, and that means that my overall derivative is going to be positive. Okay, then I have negative, positive, positive, which means that this is negative. Then I've got negative, positive, positive, which means negative, and then positive, 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 positive. Recall, I'm only looking at going across these critical numbers. So across the critical number of -3, I see I go from positive to negative, so increasing to decreasing. So that means -3, and then I sub that -3 back into here to get my y value. Negative 3.8 is a max. Okay. This one right here is a vertical asymptote. Remember, because at -1, I have a restriction, so I've got a vertical asymptote there. But over here, okay, I'm going from decreasing to increasing, so that means that 1, and I sub 1 into here, 1, 0 is a minimum. Okay, so the whole point of this example right here is so that you don't include -1 as one of your critical numbers, even though it makes the first derivative undefined. And then also make sure to include -1 in your sign table right here. Okay, last one. Find and characterize these critical points right here. Okay, so again, if I look at this, there's no restrictions on x in the function, so basically any x value could be a critical number. So I'll go ahead and find the first derivative of this. So the first derivative of this is 4 plus 16x to the power of -1/3. Okay? And so this right here, there's like really not much to show. The only thing that I can really show with this is I can say, okay, well, that's the same thing as saying 16 over the cube root of x that's in the denominator. Okay, well, if the cube root of x is in the denominator and any value of x could have been a critical number, this makes the denominator undefined, so x equal to 0 is a critical number. And because it's in the denominator, it would cause the first derivative to become undefined. So that means I either have a cusp or a vertical tangent. And if you're wondering where I'm getting this from right here, we can go back to this portion of the note. And we said that for critical points where the first derivative doesn't exist, we could either have a cusp, that's if there's a sign change, or a vertical tangent. So we're going to figure out which one it is. Is it a cusp or is it a vertical tangent? So I'll set this first derivative equal to 0. 4 plus 16 cube root of x, okay? And then I get this right here, -4 is equal to 16 over the cube root of x, okay? And then solving for x right here, I can say cube root of x is equal to -4, right? Just by rearranging this right here. And so therefore, x is equal to -64, okay? And that's a critical number, because that makes my first derivative equal to 0. So that one could be a max, min, or flat POI. I'll have to figure out which one it is. Okay, so I've got some options here, okay? I'm going to make a sign table, and so my sign table is just going to be pretty easy. I'm going to use x less than -64. Again, I include my restrictions, and then x is greater than 0. Okay, and then I can just look at my first derivative entirely. So 4 plus 16 over the cube root of x. Well, 4 plus 16 over the cube root of x, okay, which is my first derivative. If x is less than -64, that makes it positive, which means that my first derivative is positive. But between -64 and 0, my first derivative is going to be negative. And that makes my first derivative, of course, this expression is negative, so my first derivative is negative. And then for x greater than 0, it's positive, so that means my first derivative is positive. And so we can see that over 64 right here, over the value of x is equal to -64 rather, -64, I get -64 comma 128 is a maximum because it's going from increasing to decreasing. Now, this is where it was undefined. And you can see right here, there's a sign change. So that means that 0, 0 is a cusp, right? So this is the undefined critical point, or critical number, 0. And I see there's a sign change across that critical number. So that makes it a cusp. This is the critical number that made the first derivative equal to 0. There's a sign change that makes it maximum because it's going from increasing to decreasing. Okay, so a bit of a longer lesson, but overall, I think the key point to really know or to have on hand at all times is this portion right here, because it tells you what each of the critical points is. If the critical point is an x value that makes the first derivative equal to 0, then it's a max, min, or flat POI. But if there's an x value where the first derivative does not exist, then it's going to be a cusp or a vertical tangent depending on the sign changes. Okay? All right, homework is listed right there. Thanks always for watching.